Often, we are interested in functions f of t for which the Fourier transform does not exist, because your f does not approach to zero as time approaches infinity, and so the integral defining your Fourier transform does not converge. This would be the case for the function f of t equal to t, which does not possess a Fourier transform. Furthermore, we might be interested in a given function only for t that's greater than zero. For example, when we are given the value of t equal to 0 in an initial value problem. This leads us to consider the Laplace transform, your f bar of s, or your L of f of t, or of f of t, which is defined by this equation here. So your f bar of s is your Laplace transform, which is equal to the integral of f of t times the exponential of negative st dt evaluated from 0 to infinity, provided that the integral exists. In this equation, for your Laplace transform, we assume that S is real, but complex values would have to be considered in a more detailed study. In practice, for a given function f of t, there will be some real number s naught, such that this integral exists for s that's greater than s naught, but diverges for s that's less than or equal to s naught. And through this equation, we define a linear transformation of L that converts functions of the variable t to functions of a new variable s. So what we do is uh, the function of the variable t is transformed to a function of a new variable s. So you are shifting from, let's say, for example, the time domain up to the s domain. So the linear transformation L, you have your Laplace transform of a f1 of t plus b f2 t is equal to a, the Laplace transform of f of t plus b, the Laplace transform of f2 t. So this is equal to a Laplace transform, or this one now is converted into a times the Laplace transform 1 of s plus bf, the Laplace b times the Laplace transform to of s. So you are converting again the function of the variable t to functions of a new variable s here. That's what we usually do with the Laplace transform. You have a function of variable t, let's say for example a variable time, and convert this one to functions of variable s. For example, let's find the Laplace transform of the function f of t that's equal to 1. So by direct application of the definition of a Laplace transform equation, we find that you have your 1 times e, or times exponential negative st dt, wherein the integral of this one, and solve the integral of this one as your negative 1 over s e negative st, evaluated from 0 to infinity. Now, if after evaluating this one from 0 to infinity, we find that the integral is equal to 1 over s. This is true for s that's greater than 0. So as you can see, the restriction s is greater than 0 is required for the integral to exist. Now let's have another example. Find the Laplace transform of the function f of t equal to exponential at. Again, by direct application of the definition of the Laplace transform equation, we find that the Laplace transform f bar of s is equal to the integral of exponential at times exponential negative st dt, evaluated from 0 to infinity. And you can just combine these two exponentials here so that you have the exponential of a minus st dt. Finally, evaluating this integral, we find that the integral is equal to e a minus s times t over a minus s, evaluated again from 0 to infinity. If we evaluate this one, If we evaluate this function at t is equal to infinity, we find that this equation uh, approaches to zero at infinity. So you have 0 minus this function evaluated at t is equal to 0. So you have 0 minus this function here. So you have this at top, you just have equal to, or at the top, the function equals to 1. So you have 1 over a minus s. So you have 0 minus 1 over a minus s. But you can just change this one so that you have 1 over s minus a. And this is true if s is greater than a, of course. Now for another example, let's find the Laplace transform of the function f of t that's equal to t to the n, for n is equal to 0, 1, 2, up to any number. Now again, by direct application of the definition of Laplace transform equation, we find that the Laplace transform f bar n of s is equal to the integral of t to the n e negative st dt, evaluated from 0 to infinity. And you can evaluate this integral by using the integration by parts. And by integration by parts, you find that your f bar of n, or f bar n of s, is equal to this function here plus uh, this one here. Okay, so you can evaluate now this one and this one. This just flows out and becomes um, 0 plus some values here, some values of the integral here. And this is true if your s is greater than 0. We now have a recursion relation between successive transforms, and by calculating your f bar sub 0, we find, or we can also infer your f bar of 1, f bar of 2, etc. Since your t to 0 is equal to 1, we have your f bar 0 is equal to 1 over s, if of course s is greater than 0. And by recursion relation, you have your f bar 1 of s is equal to 1 over s squared. Your f bar 2 of s is equal to 2 factorial over s cubed, and so on and so forth. And you have this factorial here for any value of n. So that's just how you're going to find the Laplace transform. You just use the equation and then you do the integration. You can also use integration tables to aid you in your problem solving. However, unlike that for the Fourier transform, the inversion of the Laplace transform is not an easy operation to perform. The general method for obtaining an inverse Laplace transform makes use of the complex variable theory, and we are not going to discuss this one for this course. However, progress can be made without having to find an explicit inverse, since we can prepare a dictionary of the Laplace transforms of common functions, and when faced with an inversion to carry out, hope to find that the given transform is in the listing. Now, this is the dictionary that we are talking about. These are the standard Laplace transforms, and these transforms are valid for s is greater than s naught. So let's say, for example, if you have your f of t that's equal to any constant c, the Laplace transform is equal to c over s. Let's say, for example, if your f of t is equal to 1, you know that the Laplace transform is equal to 1 over s. So if f of t is equal to 2, then your Laplace transform is equal to 2 over s. Now, just from this one, you know that the inverse of 2 over s is equal to 2. and so on and so forth. Like say for example, we have this one here, the Laplace transform of the previous example where we have e to the n exponential at is equal to this one here. Now, if you find something or an equation of like this, and you are asked to find the inverse of this Laplace transform, you already know that it is this one here. So this table will aid us in finding the inverse of the Laplace transform, since we did not discuss, or we are not going to discuss in this course, the how do you call this, the complex variables that should be discussed in order to find the inverse of the Laplace transform. When finding the inverse of the Laplace transform using the table, it is useful to note that for all practical purposes, the inverse Laplace transform is unique and linear, so that the inverse of the Laplace transform L negative 1 of A f bar 1s plus B f bar 2 of s is equal to your A f1 of t plus B f2 t of t. So as you can see here, we can actually, if you have some function uh, where you do not find the standard of the Laplace transform, you can divide, or uh, you can transform your function into something that looks similar into your dictionary. And in many practical problems, the method of partial fractions can be useful in producing an expression from which the inverse Laplace transform can be found. Like say for example in this example, using the table for standard Laplace transform, find your f of t if your f bar of t is equal to s plus 3 over s times s plus 1. If you're going to look at the standard Laplace transform table, you find that there's no inverse of this Laplace transform here. But by using the partial fractions of f bar of t, your f bar of t may be written as the following. You have 3 over s minus 2 over s plus 1. If you're going to simplify this one, you see that this just becomes this equation here. So we just have the partial fractions of this function here. So this one here, these two functions here are actually familiar from your Laplace transform table. So let's look at the standard Laplace transforms in the table. Again, you have t over s minus 2 over s plus 1. Your t over s can be seen here using this Laplace transform here, and we know that the inverse is equal to 3. Okay, now for your 2 over s plus 1, if you're going to look at, you have 2 over s plus 1, the nearest that we can get is this function here. Now we can just multiply 2, so you have something like 2 times exponential at, where your a is equal to negative 1. This is just like 1 over s plus negative 1, right? So we'll be using this one and this one here. We find that the inverse transform of 2 over s is 3 for s is greater than 0, and the inverse transform of 2 over s plus 1 is 2 times exponential of negative t for s is greater than negative 1. And so the inverse of the Laplace transform f of t is equal to p minus 2e negative t, and this is true if s is greater than 0. So that is your your Laplace transform and the inverse of your Laplace transform.